Hello, my dear students. Let's start with a new lecture of fundamentals of digital communication. So, what are the basics of digital communication? Here you can see there is a block diagram of digital communication system. So, you can see here there is an input signal as usual. It may be analog or digital. Most probably, digital signals are very much important in that particular fact. And then it will go to the low pass filter, then the sampler, quantizer, source encoder will come. In that particular part, if any analog signal go through to this part, it will be digitized. Okay, after channel encoding, it will be digitized and go through to the multiplexer section. That means there are too many other signals are out there. That means the other signal will go through from here, go out from here, just like that will entering in different parts of the different signals. The multiplexer will just multiplex all the signals and just send it to the line encoder. We will read after the basic of the line coding. Then it will go through the pulse shaping filters that will shape the pulse, and then the carrier frequency, that means the high frequency, will enter into it in the modulated section, and it will go through to the channel. So that's the basic of digital communication system, basic block diagram of digital communication system. Okay, so when you want to find out the digital communication system, we have to think over two things. That is an theoretical, hypothetical thing. There's noiseless channel. In practical purpose, there is no noiseless channel that literally exists in Earth or in communication systems over the Earth, over the cosmic reality. But we have to assume a noiseless system. That means the ideal characteristics. So there are noiseless channels, and Nyquist theorem is that. The Nyquist theorem is imposed for the noiseless channel. Okay, so Nyquist theorem is for a noiseless channel. For a noiseless channel, Nyquist theorem gives the relationship between the channel bandwidth and maximum data rate that can be transmitted over this channel. That means, for a noiseless channel, the Nyquist theorem gives the relationship between the channel bandwidth and the maximum data rate that can be transmitted over the channel. It is considered the noiseless channel when we use the Nyquist theorem. In that particular thing, he states the relationship between the channel bandwidth and maximum data rate that can be transmitted over this channel. What is the relationship between these two? Let's see. So that is the relationship. That is the relationship of Nyquist theorem. So in that particular thing, that is capacity of the channel is twice of the bandwidth and logarithmic part of the number of finite states in a symbol of transmitted signal. So that's the thing. The Nyquist theorem. Okay. So that's the noiseless channel. So there are a lot of examples out there in that particular thing. That's the noiseless channel with 3 kilohertz bandwidth can only transmit a maximum of 6 kbps. That means twice of the bandwidth. Literally no loss are there. That means twice the bandwidth, and log 2m, that means number of finite states and symbols. We will learn it after the lecture, after the lecture course, or after the course to do it. So that's the thing. And can only transmit a maximum of 6 kbps if the symbols are binary symbols. Okay. So that particular thing. So the binary, if it is the binary symbol, that is 0 1 0 0 1, whatever it is. So if you get the two binary states, so 0 or 1, that means you got 4 levels, 4 number of finite series. That means 0 0 0 1 0 1 0 1 1. Okay, 2 to the power 2. If you get three binary states, which is 0, 1, 0, what can I just combination of the figures 2 to the 3? So that will be 8 type of finite levels. So that can be state here. So here we can see that is the Nyquist minimum bandwidth. What is the Nyquist minimum bandwidth requirement? The theoretical minimum bandwidth needed to be baseband transmission of a symbol RS symbols per second is RS by 2 Hz. That means if we want to get the highest possible capacity, so the first thing we have to keep on our mind that it should be the twice of its bandwidth. When we get the twice of its bandwidth, then our symbol per second will be dropped down to half. That's the reciprocal theorem. As you know, the frequency is reciprocal to the time period. So that is why we get through both of these. So there are two signals. There is a frequency spectrum. That is the spectrum of a rectangular signal that has been transferred to the sync signal. How can we look at it? That is the frequency. That is the frequency block. So whenever you convert the frequency plots to the time plots, we need to have the Laplace theorem. You impose the Laplace here, you can get the time sequence for this particular frequency sequences. That is the thing. Okay. So what is Shannon's bound for noisy channels? The first thing, go to the previous lecture, get here how the wheel converts. Okay. Now that is the Shannon's capacity theorem. Okay. So there is a fundamental upper bound on achievable bandwidth efficiency. Shannon states that there is a particular type of noisy channel, the noise in environment or in digital communication channel. Okay. So in Shannon's bound for noisy channels is the relationship between the noisy channel. In previous section, when we go through to the Nyquist theorem, there is no noise involved there, but practically in every part of channel, noise really exists. So we can't ignore the noise section. Okay, we have to put the noise there. If we not just accept or we can say we cannot transmit a signal without noise, so we have to consider the noise that Shannon states, and that is the Shannon's theorem. It is the most popular theorem in digital communication or communication systems or wireless communication. Shannon's theorem gives the relationship between the channel bandwidth and the maximum data rate that can be transmitted over the noisy channel. The relationship between these things is that the capacity. If you want to find out the capacity, the C will be B log 2 and rest of this NB max, what are there is NB max. Okay, the maximum capacity, the maximum data rate, that's NB max, that can be transmitted over a channel is log 2 1 plus SNR, signal to noise ratio. That is the signal to noise ratio, or SNR. That's the signal to noise ratio, that is SNR, as you can see here. So C is the channel capacity, B or W would be the RF bandwidth, you can say, and if you want to find out the channel capacity, it will be 1 plus SNR, log 2. The base of the log is 2 because it really finds out the binary digital data. So the base will not be 10, the base will be 2. Okay, to find out the channel capacity, the maximum channel capacity, the maximum bit or data rate can be transmitted over the noise channel if it is proportional to the bandwidth and proportional to the logarithmic, the two base logarithmic of the signal to noise ratio with 180. That's the thing. That's the Shannon's bound for noisy channels, and that is for the first lecture of our digital communication. Thank you very much.